Hi everyone, welcome back. In this video, we will look at what is called Adler's equation. So we'll derive this result from the basics and uh, and we'll look at the implications of Adler's equation. Okay, so this is a continuation of the injection locking video from the last one. Hopefully you watched that. So before we get started, let's do a quick review of the definitions. So I'll just make a few definitions, which will hopefully clarify things as we go along. Okay, so we'll define omega as the instantaneous, what's wrong? The instantaneous frequency of the oscillator after injection. So after you've injected a sinusoidal signal, when it is kind of undergoing lock or even after locking or when it's being pulled, this is the instantaneous frequency. Okay. And then omega injection is the frequency of the injected signal. Frequency of injected signal. Omega naught is the free running frequency before locking or before injection. The free running frequency that is before injection. Okay. Then phi naught is the phase difference between the vector of IT, right, and vector I oscillation. If you don't know what these are, we discussed them in the last video. Okay, and this is also, and it is also the phase shift of the tank, right? So if you watch the last video, you know that the tank phase shift kind of is such that, sorry, the phase shift between IT and I oscillation is such that it has to undo the phase shift of the tank. So they're equal. Okay, here I'm kind of ignoring that 180 degrees part of the tank, which doesn't really matter. You can just change the definition of IT and that 180 factor should go away, but we'll see that it doesn't really matter. Okay, so I'll call it the phase shift of the tank. And then we have another definition, which is theta. And that is the phase shift between I oscillation, phase difference between I injection and I oscillation. Okay. All right, so we pictorially kind of drew this last time. We said that if I have an injected signal, which is as a phasor like this, so this is I injection, and then you have I injection plus I oscillation is, so I'll say, okay, I oscillation is like that. Say it's like that. Then IT should be like this. And this is IT, this is I oscillation. And then we'll kind of define those angles that we just defined, or we'll write down those angles that we just defined. So I oscillation, if I draw it from here, it's something like this. Right, this is I oscillation from, have the same base basically. And then we said this is phi naught, and this whole thing is theta. Okay. All right. Very good. So now let's go ahead and actually do the derivation of Adler's equation. Okay, so step one is pretty simple. So we said theta is basically this is the phase difference between I injection and I oscillation, right? So that is the phase of the injected signal minus the phase of, oh, sorry, it's the phase of the oscillator minus the phase of the injection signal, right? So the phase of the oscillator minus the phase of the injected signal. So which means that d theta over dt is nothing but omega minus omega injection, right? Where omega is the free running, not free running, it's the oscillator's instantaneous frequency after injection, right? That's what we just defined, which is this one. And omega injection is this. So that's just the definition of the instantaneous frequency, right? It's the derivative of the phase. So I take the derivative of theta, I get basically this. So this will be our first expression. Okay. All right. And then step two is we'll just use some geometry. So I'll copy this. So let's copy paste this, right? So now you can kind of see that if we can extend this a little bit, right? This angle is also phi naught, right? Because this angle is phi naught. So that is phi naught, and then you have this angle is theta, right? So from the law of course, a law of sines, we can say that I injection over sine phi naught is equal to t over sine of 180 degrees minus theta, which is the same thing as it over sine theta, right? So which means that I can say sine phi naught is equal to I injection over it times sine theta, right? And then from law of cosines, earlier we used law of sines, now we use law of cosines. We can write this as I injection sine theta divided by square root of I oscillation square plus I injection square minus 2 times I oscillation I injection times cosine theta, right? So that's the law of cosines, like a generalization of Pythagoras theorem. Okay, and then we make this assumption that, so we assume that the injection signal is weak, right? So if we assume I injection is much smaller than the amplitude now, than I oscillation, which means that IT is very close to I oscillation, right? If I injection is small, then these two would basically kind of be very close to each other, right? Which means that phi naught would be a very small angle, right? So that means that sine phi naught is approximately phi naught, right? Because phi naught is small. And the denominator is approximately just I oscillation, right? Because I injection is small, so this term is small and this term is small. So you're only left with this really, right? Okay, so we can simplify this as saying phi naught the left-hand side is now phi naught, and the right-hand side is I injection over I oscillation times sine theta, right? Okay. So call this equation 2. Okay. So now what do we have? We have a relationship between theta and phi naught. And we also have a relationship between the injected signal frequency, the instantaneous frequency, and the phase shift between the injected signal and the oscillation signal, right? So what do we need? We have one missing piece left, right? So we don't know what is the relationship between omega, the oscillation frequency, and phi naught, right? If you have that, then we can put phi naught in here, and then we get what we want, theta versus phi naught versus omega injection, right? From these two relationships. And that's exactly what Adler's equation is. So to bridge that gap, what we want to do is we want to derive an expression between the frequency of oscillation or the offset frequency from the free running frequency and the phase shift phi naught between I oscillation and IT. And to do that, we realize that phi naught is also the tank phase, right? So we do know when you move away from the resonance of the tank, how phi naught changes with frequency. So that's what gives us the last piece of the puzzle. Okay, so let's do that. So if I have a second order parallel LC tank, right, then you can derive the phase as a function of frequency to be tan inverse of R over omega L times omega naught square minus omega square divided by omega naught square. So that's, you can find that in circuits textbooks, I guess, or you can also derive it yourself. But essentially, you want to look at the phase, the impedance of the tank, and then look at the phase of that impedance, and you can show that this is the expression. Okay, so with this expression in mind, if I look at what this looks like, it looks something like this. Right, and that's kind of what we assumed earlier as well. Right, so here you have omega naught, this is omega, and this is phi naught. Okay, so now if we assume, okay, that make another assumption, which is that if omega is close to omega naught, right? So if you're close to the free running frequency, you're injecting close to it, which is a valid assumption, then you can approximate this as a straight line. So that's sort of taking the Taylor series approximation around omega naught and just taking the linear component of it. Okay, so if you do that, so I'll say if omega is close to omega naught, right? Which means that you've injected, omega is not exactly the injection frequency, but you can assume that omega is close to the injection frequency. Then the phase shift that you experience is going to be, as long as you inject close to omega naught, then that's basically linear, right? Okay. And when it's linear, tan inverse of this is essentially just the function itself. Right? Because obviously, I mean, we know that I mean, what I was trying to say is that we know that tan inverse of x is approximately equal to x, right? So that's what I'm kind of using here. It's a linear approximation of the tan inverse function. Okay. So which means that phi naught now is approximately equal to, one more thing to mention is that this is just the Q of the tank. So we'll use Q instead. So phi naught is Q times omega naught plus omega times omega naught minus omega divided by omega naught square. And this is approximately equal to 2 omega naught, right? So that cancels with this, and then you're left with Q times omega naught minus omega times 2 over omega naught. Okay, very nice. So now we have two different expressions for phi naught. We have this expression for phi naught, and we also have this expression, right? So we just equate them. So let me call this down. And then this becomes phi naught. This is number 3. Okay, so then equating 2 and 3. What do we get? We get I injection over I oscillation times sine theta is equal to 2q over omega naught times omega naught minus omega, which is, so here's the trick. So I can write this as 2q over omega naught times omega naught minus omega injection minus omega injection, right? Just adding plus or minus omega injection in there. Okay, and then we know that this is nothing but d theta over dt, right? So from that, we can rearrange the terms in here, and that will give us the final expression. So let me just write one more step. Omega injection over omega oscillation times sine theta is 2q over omega naught times omega naught minus omega injection minus d theta over dt. Right, so that's now a differential equation. And you can rearrange these terms to give you d theta over dt is omega naught minus omega injection minus omega naught over q times I injection over I oscillation times sine theta. So that's the final result. This equation is called Adler's equation. Okay, so what is it, right? It's called Adler's equation, but what it really is, it's describing the dynamics of theta as a function of many things. It's a function of the free running frequency, the injected frequency, the quality factor of the tank, the injected signal's current strength, or the strength of its the signal, the oscillators, free running oscillators amplitude, and yeah, that's it. And then you have theta on the right? So it's a differential equation essentially. So this is a differential equation describing the dynamics of theta as a function of time. Keep in mind that we haven't really assumed here that anything is locked, right? So we just said that you are injecting a signal, the frequency of that signal, so you're injecting at omega injection, that causes some perturbation to the oscillation frequency, which now is given by omega, which is the instantaneous frequency of the oscillator under injection. And that was the only really assumption. And we said that, okay, the injection signal is small and so on. And this is the final dynamics, right? So we haven't really, this is describing both injection locking and injection pulling. It's a general equation that describes both those phenomena. Okay, so let's see what are the big insights, right, from this. So the first insight is that when you achieve locking, right, theta is constant. And so once it's locked, the phase of the oscillator as a function with respect to the injected signal is fixed, right? That's what we talked about in the last video. And when theta is constant, implies that d theta over dt is 0, right? So you get sine of theta is equal to 2q over omega naught times I oscillation over I injection times omega naught minus omega injection, right? So that's also an important relationship. And this exactly tells you if you inject at a specific frequency, omega injection, what would be the final resulting phase shift between the oscillator after it's locked and the injected signal, right? So that exactly describes that relationship. And that's very useful actually if you want to design when you deal with injection locking. It's a very useful expression. Okay, so under the locked condition, this is what you get. Sine theta is given by, or theta, the phase shift between your locked oscillator and the injected oscillator is given by this expression. So it's a function of the quality factor. It's a function of the ratio of the injected amplitudes, or the ratio of the injected signal and oscillation amplitude. So it makes sense, right? I mean, for example, if your injected signal is very strong, then the phase shift that you see is smaller. Yeah, right. It's closer to the injected signal then. Okay, so the second big insight, this move on. So we see that sine theta can only be between -1 and 1, right? Which means that locking can only occur within a certain range. Because the left-hand side is bounded, so the right-hand side should also be bounded. And that range is called the locking range, right? Which is given by omega injection minus omega naught. So I'll call this the positive locking range, right? When sine theta is equal to 1. This is equal to omega naught times I injection over 2q I oscillation, which is also equal to minus omega L minus, right? The lower part of the locking range. And we see that the locking range, at least with this derivation, is symmetric. We'll see in future videos that that's actually not entirely true. We'll talk about the limitations of Adler's equation and Adler's model. But for now, we see that it is symmetric. And if you want to look at the double-sided locking range, which is the entire locking range, and we normalize it with the free running frequency, because obviously, you want to see the percentage of locking range as a function of free running frequency. That is I injection over Q times I oscillation. This is also a very useful result. So essentially, if you have a very strong injected signal, the injected signal is strong, then the locking range increases. And if the quality factor is high, the locking range actually decreases. Right? I mean, you can't really lock to an ideal oscillator, which doesn't have any quality factor. Essentially, if the quality factor is infinity, you can't lock to that. And we'll kind of discuss the dynamics in more detail in future videos and see why that's the case. But intuitively, basically, if my oscillator has some phase noise around it, right, which kind of follows the cue of the tank, not exactly, but kind of, then you need to make sure that your that your injection signal is stronger than this, right? Only then it can really lock, right? I mean, if it's below the phase noise, obviously it's not going to see it because it has its own phase noise kind of dominates that locking signal, right? So if the Q is higher, then this one's phase noise would look like this. And now even with a weaker signal, you can kind of lock it, right? So now this signal is above the phase noise. So that's kind of the intuitive picture, I guess. And of course, it depends on the ratio of I injection to I oscillation, right? So if your oscillator is very strong, huge amplitude fluctuation, amplitude variation in the oscillation, then the injected signal has to be even stronger, right, to lock it. Okay, so that's kind of the derivation of Adler's equation. This is a simpler derivation than some of the stuff I've seen out there, but This is very close to actually what Adler has in his original paper, which I'll leave in the references below. I've just changed the notation a little bit to be more up to date with some of the more recent publications. Okay, so one thing I should mention definitely is the limitations of Adler's model. Okay. Okay, so the first limitation is that it only deals with weak injection, right? So what happens if you inject a strong signal? You can actually kind of modify Adler's equation and show that you can introduce a term in here in the denominator essentially of this part. And then when you change this, you can include the amplitude, uh, the effect of large injection as well. It doesn't change that much, but still, right now the equation that we've derived kind of doesn't account for that, right? Okay, so we've also only so it's kind of limited to LC oscillators, right? So in this derivation at least, and even in Adler's original derivation, he kind of assumes that it's an LC oscillator. It has a specific Q quality factor, right? And he derives it that way. But this phenomena of injection locking goes way beyond uh, even electrical oscillators. It shows up in mechanical oscillators, in neuroscience, in weather patterns, things like that. So it's literally everywhere. Um, you need to have essentially just an oscillator, and it will show you this kind of behavior. So second order nonlinear differential equations that have stable limit cycles will exhibit uh, injection locking. It's a very general phenomena, but okay, here we've limited ourselves to LC oscillators. But again, even within electrical oscillators, we don't know, we haven't really looked at what does Q mean for a ring oscillator, right? Or some kind of other multi-stable or astable multivibrators, things like that. So um, it's more general. Okay, that's another kind of drawback. And then we said that uh, it predicts a symmetric locking range, right? Okay, so that is also in general not true, and there are some papers that have shown that you can have injection locking without a symmetric locking range. So this model doesn't really talk about that, and one of the reasons is that it's another one of the drawbacks. It's one of the reasons is that we assume a sinusoidal injection, right? That's one of the reasons. Another reason is that um, we've assumed it's like an LC oscillator with a very pure sinusoidal signal, right? We haven't really looked at a nonlinear model of this, or even a time varying model, really. So what happens if your injection signal is not a sinusoid, right? What if you inject a square wave or some other shape wave? What happens? We don't have to do that with Adler's equation. So that's another one of the drawbacks. And one more drawback is that you kind of need to know what Q is, right, for your oscillator, or even what I oscillation is. Now, of course, in simulation, you can get I oscillation fairly easily. Q, you may not be able to get that easily because it's inside a circuit, right? So you can get the Q of an isolated resonator, but when you put it inside the circuit, it changes. You have all these parasitics and everything. And anyways, when you actually make the oscillator from PVT variations, these things will change, and it will be very hard to actually probe it and see what these values are without changing them. So these factors of I oscillation and Q are kind of hard to determine, right? So that's kind of another drawback. So these are the limitations, I would say, but it's still a very powerful model. It's a very, very old paper, and there have been many improvements to these models, which we'll discuss in future videos. Actually, we'll see how we can use PPV and ISF, both those concepts to kind of generalize Adler's equation a little bit. And we'll also look at some other really interesting works on using more nonlinear models and how quadrature oscillation is generated, things like that. Yeah, I'm excited about that as well. All right, so in the next video, what we will do is we will look at the solution to this differential equation to actually see when you're beyond the locking range, what does injection pulling look like? It's very important to know that, because when you're doing experiments, sometimes you may see something on the spectrum analyzer and you don't know what it is, but turns out it's injection pulling. So if you know what injection pulling looks like quantitatively on the spectrum analyzer, or even behaviorally what it is, it could be very useful when you're doing experiments. So that's what we'll do in the next video. All right, hopefully this was interesting. Leave any comments that you have. I'll upload the notes and I'll see you in the next one. Thank you.